Hello friends, this is Professor Rahul Bhavani, and today for the subject of heat transfer, we are going to see Fourier's law of heat conduction. And now the basic concept of driving forces. In this picture, as we see the water is flowing. So what is the driving force for this water? So it is always a height difference. So water is always a flow from high level to low level. Second picture showing the wind flow. For wind flow, the driving force is pressure difference. So wind is always flow from high pressure region to low pressure region. In the same way, for heat flow, so the driving force which is responsible for heat flow is a temperature difference. So heat is always flow from high temperature point to low temperature point. Now the Fourier's law of heat conduction. Suppose we are considering one slab having a thickness dx, and this slab is masked all over. Only the center portion of this metal slab is open for heat transfer. And this slab, one face is maintained at T1 temperature, second phase is maintained at T2 temperature, and T1 is higher than T2, so heat will flow from left face to right face. But as it is mass all over, so it will flow through only the center portion. And here we are considering only unidirectional heat flow, that's means along the dx direction. So the temperature difference which is responsible for heat flow through this slab is dt. Now imagine heat is flowing from left face through the open portion and travel through this slab through the distance dx, that is called heat flow path. Many times dx is denoted by length of path L. So friends, whatever be the heat transfer take place, it is depend on the temperature difference. So if temperature difference is more, then more heat transfer will be there. In the same way, if it is depend on length of path, so if length of path dx is more, then heat flow rate will decrease. That means heat flow rate is inversely proportional to length of path, but it is directly proportional to temperature difference. So more temperature difference, more heat transfer will be there. Now suppose that center portion which is responsible for heat transfer, it area is increased. So as we increase the area, so more heat will transfer from this slab from same temperature difference, but heat flow rate will increase as we increase the area. This area is a cross sectional area, or it is called as a area normal to the direction of heat flow. That means heat transfer rate depends on area also. If area is increases, heat transfer rate will increases. So we have three parameters, that is dx, temperature difference dt, and area. So linking to heat transfer rate q, so we can say that heat transfer rate is directly proportional to area. Obvious that area is a cross sectional area, or area normal to the direction of heat flow. Q is again directly proportional to dt, temperature difference, but it is inversely proportional to dx, that is the length of heat flow path. If we remove the proportionality sign, then it become q is equal to minus ka dt by dx, where k is the constant of proportionality and known as a thermal conductivity of that body or material. Now, what about the minus sign? Minus sign. So, dt, we always consider dt, that is temperature difference, that is T2 minus T1. But as heat is flowing in a direction of dx, T1 is higher, T2 is lower. So, the temperature difference T2 minus T1 gives the negative value. To compensate that negativity, negative sign is incorporated in the formula. So q is equal to minus ka dt by dx. So negative sign compensate that negativity of temperature difference T2 minus T1. Now mathematical expression for Fourier's law. So expression of Fourier's law, q is equals to, sorry, q is directly proportional to area, cross sectional area, and dt by dx. This dt by dx many times directly called as temperature gradient. So q is directly proportional to area as well as temperature gradient. Now dt, temperature difference across the thickness, and it is always T2 minus T1 along the heat flow path. So as T2 is lesser than T1, so it gives always negative value. So to compensate that negativity, we use a minus sign. So if we remove the proportionality sign, q is equals to minus ka dt by dx. So as we can see in a picture, that heating point where temperature is T1, and after dx distance this temperature drops to T2. So T2 minus T1 always gives negative value. Now if we consider temperature difference as T1 minus T2, so it gives positive value. Then there is no need of a negative sign, or in other way we can say, if we remove common negative sign in a dt, then negative negative get cancelled and it become q is equals to ka dt by dx. So remember friends, whenever there is a minus sign in an expression of Fourier's law, it means we consider dt as lesser temperature minus higher temperature, and if there is no negative sign, it means we consider dt as higher temperature minus lower temperature. So we have this expression, q is directly proportional to cross sectional area and temperature gradient. From this expression we can write the definition of our Fourier's law of heat conduction. So remember, from this definition where proportionality sign is used, we can write as a write its definition. So Fourier's law of heat conduction is defined as the rate of flow of heat through a simple homogeneous solid is directly proportional to the area of the section at normal to the direction of heat flow and to the change of temperature with respect to the length of path in the direction of heat flow per unit time. Obvious time limit should be there, so per unit time. Another definition for Fourier's law, it is defined as the rate of flow of heat through a solid is directly proportional to the cross sectional area of the section and the temperature gradient in the direction of heat flow per unit time. So many times we can elaborate dt by dx separately, or we can combinedly called as temperature gradient. Now what are the assumptions we considered during deriving this Fourier's law equation? So assumptions are: first, conduction of heat take place under steady state condition. So what is the steady state condition? Steady state conditions means there is no temperature changes even though we heat that object for more time, but its temperature remains same. So temperature remains same with respect to time is called as steady state. So first assumption, we consider steady state condition during deriving this Fourier's law of heat conduction. Second assumption, we consider heat flow in unidirectional only. In a derivation animation, we saw heat is flowing only along the thickness of slab, not in a radial direction, not in a vertical or lateral direction. It is along only the length of or thickness of slab. So we only consider unidirectional. So just like this, only unidirectional, not in a radial direction. The temperature gradient is linear and constant. What it means? So temperature gradients, that means drop of temperature is linear. So if I divide the length of heat flow path in equal length, then each segment showing the same temperature drop, that is linear one. So it is assumed that the temperature gradient is linear and it is constant. There is another assumptions, there is no internal heat generation. In many applications, just like a plutonium or uranium rod application, when it is bombarded, then it generate heat inside. So we are assuming there is no uh, heat generation source inside the material or object, even though in electrical cables, when current is passing through any electrical cable, so it generate heats and that cable get heated. So such kind of phenomena we are not considering. So this is again assumptions. Another is the material is homogeneous and isotropic. So homogeneous, this is the image of wooden block cut section. So here we can say that this material is not homogeneous. It is layer by layer by layer, and so it is not called as a homogeneous. So whatever be the assumptions we assume during deriving this Fourier's law, we assume the material is homogeneous. That means everywhere the grain structure is same. And isotropic, so isotropic, so it means the material having same thermal conductivity in all direction, which is not the exact case, actual case, because thermal conductivity is different in different direction because of its grain structures. But here we assume that it is homogeneous and isotropic. Another assumptions, the bounding surface are isothermal in nature. So we are considering heat is flowing through one direction only, suppose along the lane. So whatever be the surrounding surface which is bounded by any insulation material, then it is isothermal in nature. This is again a assumptions. So these are the assumptions. Next is the property thermal conductivity, that is K. So Q, that is heat transfer. Here we are talking about conduction, so suffix conduction, COND. So Q conduction is equals to minus K, where K is thermal conductivity, cross sectional area, and dt by dx. Now suppose there is not mention a minus sign for k, it means we are considering dt as higher minus lower, so t1 minus t2. Now we are interested in finding the thermal conductivity, that is k value. So in above equation we are shifting all remaining value to second side, so k becomes equals to q divided by area multiplied by dx upon dt. Always remember when we are talking about Fourier's law, so area is always a cross sectional area. Now from this, what we define thermal conductivity, K is defined as the heat conduction rate per unit area normal to the direction of heat flow through unit thickness of the body per unit temperature difference. So whatever be the notations we are observing in a formula of k, q divided by area multiplied by dx upon dt. So we can just convert into the sentence and it become a definition of thermal conductivity. So thermal conductivity is defined as the heat conduction rate, that is q, per unit area normal to the direction of heat flow, that means cross sectional area, through unit thickness, it means dx of the body, and per unit temperature difference, so dt. Now the unit of thermal conductivity, if I put all the units for above quantities, so it become watt for heat transfer rate, area it become meter square, dx in meter, and temperature difference. Remember friends, this is temperature difference, so temperature difference either in degree centigrade or kelvin, it remains same, difference quantity will be same. So unit become k, that is thermal conductivity, its unit watt divided by meter square into meter divided by degree centigrade, or it might be a Kelvin. So meter square and meter get cancelled. So final form is watt per meter degree centigrade or watt per meter Kelvin. This is very important formula, unit. So remember this. So thermal conductivity having a unit watt per meter degree centigrade or watt per meter Kelvin, and it doesn't matter whether temperatures kept in degree centigrade or Kelvin, dt remains always same. Now the significance of thermal conductivity. Thermal conductivity is the property going to describe ease with which transfer the heat from one point to another point. It plays a very important role in steady state heat conductions. So knowing the value of thermal conductivity, one can categorize material into two categories broadly, of thermal conductor and non-conductors. So next significance is higher the thermal conductivity, faster the heat is going to transfer between given 2 points, and generally all metals are good thermal conductors, for example copper, aluminum, iron, etc. And lower the thermal conductivity, slower the heat is going to transfer between given 2 points, and generally all non-metals are bad thermal conductor, hence use as thermal insulator, for example wood, asbestos, plastics, etc. So in short, thermal conductivity can use to identify whether that particular material can be used as a conductor for heat transfer or as an insulator to restrict the heat transfer. Now the another parameter, important parameter, is thermal diffusivity. Thermal diffusivity, the heat conduction rate per unit area normal to the direction of heat flow through unit thickness of body per unit temperature difference, and its unit is watt per meter Kelvin. So as we see, just what is the thermal conductivity? So thermal conductivity K. Next we required heat capacity. We are first seeing different parameters which is required to calculate thermal diffusivity or to define the thermal diffusivity. So we require mainly two parameters. One is thermal conductivity, which we just see in details. So thermal conductivity K, its unit watt per meter Kelvin, or it might be a watt per meter degree centigrade. Second parameter we require, that is heat capacity, which is the product of mass density of material and the specific heat of the material. So Cp, everyone knows well what is Cp, specific heat, or Cv, again specific heat at constant volume, specific heat at constant pressure. So Cp, it is Cv and Cp are the well known terms. And density, specific heat, many time it is not suffixed by p, it is simply written as c. So specific heat and heat capacity, what is the difference between this? Specific heat and heat capacity both are representing heat storing capability of the material, but specific heat express heat storage capability in terms of per unit mass, that is joule per kg Kelvin, and heat capacity expressed in terms of per unit volume, so joule per meter cube Kelvin. So this is the only difference in specific heat and heat capacity. Both are heat storing, showing the heat storing capability of material. One shows in terms of per unit mass, second shows in terms of per unit volume. Now the thermal diffusivity. For thermal diffusivity, we must understand what is thermal conductivity and heat capacity. Now the thermal diffusivity. Thermal diffusivity is defined as the ratio of thermal conductivity of the material to heat capacity of the material. So mathematical expression, thermal diffusivity is thermal conductivity upon heat capacity. Formula become K upon rho Cp. Many time it is denoted by K upon rho C, capital C only, and thermal diffusivity denoted by alpha. The unit of thermal diffusivity is, now if I put all the unit of all notation, K is in watt per meter Kelvin, rho kg per meter cube, and C or specific heat in joule per kg Kelvin. So in denominator kg get cancel. Watt, if I put watt as a joule per second, so numerator and denominator joule again get cancel. Kelvin, Kelvin, numerator and denominator both Kelvin get cancel, and numerator and denominator meter cube and meter, so it get cancel and remains meter square. So final form for unit of thermal diffusivity is a meter square per second. So thermal diffusivity meter square per second. Now what is the significance of thermal diffusivity? Thermal diffusivity expresses the rate at which the heat generated get diffused out. It plays a major role during transient heat conduction. So remember, thermal conductivity plays a major role in steady state conduction, and thermal diffusivity plays important role in transient heat conduction or heat transfer. The larger the value of alpha, that is thermal diffusivity, the faster will be the heat diffuse through the material and its temperature will change with time. This will result either due to a high value of thermal conductivity or a low value of heat capacity. So if you want higher thermal diffusivity, then that material must have higher value of K as well as or lower value of heat capacity. A low value of heat capacity means less amount of heat entering the element would be absorbed and used to rise its temperature, and more would be available for onward transmission. In short, it is showing that whatever be the heat transfer into the element, if thermal diffusivity is less, then maximum heat will be remain inside only and it will not transfer to second side, because thermal or transfer or diffuse outside, because thermal diffusivity is less. The non-metallic solid and liquid respond slowly to temperature change because of their relatively small value of thermal diffusivity.